for postdoctoral research. And he became assistant professor in Tsinghua University in 1997, and now he is the full professor over there. Talking about this, his project COSI. This is the compact gamma ray image detector. Actually, mainly they produced by his colleague in Taiwan. I remember his project was kind of symbol of unlucky. So maybe my the recollection was correct, because after they succeeded the first flight in the Fort Sumner in the 2009 for 38 flight, and they failed. They became very famous because of failure of the balloon launch in Australia in 2010, and then even after that, in the 2014, they had very short, the brief, the accidental, the short flight in the Antarctica. Okay, at that time, I was, thinking, oh, they are really unlucky, and maybe they cannot do anything. They could not do anything anymore. But surprisingly, okay, they just continue their effort, and then this year they succeed. This very wonderful flight for the 47 days of flight, from New Zealand. Okay, so I think today it will be very extremely educative. Okay, it's showing that this experiment is never give up. Okay, so now we are about to hear their great journey and achievement. Okay, let's the warm welcome them.
All right, thank you, Jiu, for this wonderful introduction. I just realized we are symbol of unlucky. Okay, anyway, it's my great pleasure to be here to report to you about the current status and the future of this project, this COSI project, the Compton Spectrometer and Imager. This project, okay, I should say, I just realized during lunch that later at 3:20, there. 3:30. Okay, now I get 10 minutes more. Yeah, there will be another even more important activity here in this building. So I will try to cut my talk short. All right. So this project is a project to build an instrument to detect MEV gamma ray photons from outer space. Okay, and then I will show you the collaboration now, because this is international collaboration, mainly led by UC Berkeley. So the title, the Compton Spectrometer and Imager, so we call it COSI, and it was formerly known as the Nuclear Compton Telescope Project, NCT. And we changed the name 3 years ago in 2013, because at that time we planned to have a balloon flight in Antarctica. And that is the flight Jiu just mentioned, okay, a short flight. Anyway, but when we were planning, and NASA told us that, well, the name NCT is not quite good. Why? Nuclear. NASA doesn't want to see any word related to nuclear, nuke, and so on in their brochures, yeah, this kind of thing. So okay, fine. So we changed the name. So after some discussion, the collaboration decided to change the name into the Compton Spectrometer and Imager. So for the abbreviation, certainly should be CSI, right? Okay, that's a good one. CSI. Well, somehow some people don't like it either. We probably should not say CSI Hsinchu or CSI Berkeley. So okay, then we take another letter here, COSI, CO somehow, COSI. Okay, so that's why we have this name of the project. Okay. So it is currently a balloon-borne project, because as I said, we are trying to build an instrument to detect MEV gamma ray photons from outer space. Eventually, we want to put it on some satellite, like some space telescope kind of thing. But before that, we have to demonstrate the technology that we use is reliable, yeah, so that we can go to space. And therefore, we use balloon to have some testing flights. Okay, so it's a prototype for future Compton Telescope Space Mission. I'm Hsiang-KuangChang from Institute of Astronomy, National Tsinghua University. And the message that I want to convey to you is that there is an Institute of Astronomy in National Tsinghua University. Okay. Some days ago, during the lunch in Tsinghua University with some other colleagues, from other departments, and some of them were surprised that our university has an Institute of Astronomy. Gosh, some days ago. Okay. All right. So, can we turn off some lights, or is it easy? Yeah. So what's this? This is for audience from maybe from fields other than physics. I heard that this is a joint corrugate. Turn off light here in the front, not in the back. They will fall asleep very soon. Okay. Thank you. I think that's good enough. That's good enough. Thank you. So what's that? Sound. Good. I'd like to have some response. Otherwise, not only the audience, but also the speaker will fall asleep. Okay? Yeah. So this is our sound. So very good. We are living on the same planet. This is our sound. And this is also our sound. So as you can see, our sound can be very different in different electromagnetic wave bands. Okay? And the previous one was taken, say, in X-ray or ultraviolet, extreme ultraviolet. And this is optical light. So that's why in the universe, we need to collect different informations from different wavebands, and even from different information carrier like neutrinos, like gravitational waves. And within electromagnetic waves, we have different wavebands from radio to very high energy gamma rays, right? And they all carry different information to make us understand better all the system that we want to study. All right. So, and then again, this is very fundamental. I'm talking about MEV gamma ray photons. So in order to detect MEV gamma ray photons, we need to go to space because the atmosphere is not transparent to most of the electromagnetic wave. The only two windows which are transparent are optical light and radio light. Okay, so we need to go to space. That's why I mentioned that we eventually want to go to space. Okay. All right. So the previous three slides are particularly for those from other fields. I hope there are some. Okay. Anyway, because the organizer told me this is a joint program. So, what do we want to study in the MEV universe? I said in different wavebands, we can have different information which are quite important for us to have a comprehensive picture of the system that we want to study. And in particular for this talk, because I'm talking about MEV photons. So here I will try to describe to you some relevant science that we can do. Our instrument is a general purpose instrument. That is, it's simply a detector to detect gamma ray, MEV gamma rays. That's it. So in the MEV gamma ray universe, usually, if we want, we can try to classify them into three kinds of things. One is line emission, another one continuum, and then a third one, very special, polarization measurement. In line emission, here I only mention two major issues. One is that if you take an image of the whole sky at 511 keV, this energy, you will see a picture like this. This is whole sky, and then this is the direction to the galactic center, and this is galactic plane. So you will see a very bright object or a very bright region in the direction of our galactic center. So what's wrong? Why there is such a strong emission, 511 keV emission there? So that's an issue, right? And in some other talks, I will ask the audience, what's special for this number? But here, I think most of you know that's the energy of electrons. So this line represents the annihilation of electrons and positrons. So they make 511 keV lines. So now the question is then, why are there so many positrons there in or surrounding our galactic center? We have a supermassive black hole there. Is it doing anything special or what? So there are a lot of astrophysical models to explain this, but still it's controversial now. And there are also some particle physics models, light, dark matter, decay, blah, 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 and so on. Okay. So if it can be the signature of some light, dark matter, that would be wonderful. We love it, yeah. But before reaching some more reliable theoretical models, we need more observations to make a more reliable image and also the spectral line shape of that line. Okay, I will not show you that line, but that would be into too much details. So this is one important issue. We don't know what's going on there. That's the issue. Okay, and also another thing is that in the MeV range, in the universe, there are a lot of nuclear lines. Nuclear lines. One great achievement in the last century of nuclear astrophysics or of stellar astrophysics is that we realize, we understand that all the elements heavier than helium are produced in some nuclear reaction in stars or in the very late stage of a star, and then through supernova explosion, those things are pulled out to the interstellar space, and then star forms again, and then we have those kind of heavy elements. Okay. That's a great, beautiful theory. And then, during the process, particularly for supernova, we should be able to see evidence of that theory, right? So there are many lines. There are many lines that one expects to see during a supernova explosion. I'll tell you what, up to now, there are only two weak detections, two examples of weak detections. So that great theory, a very beautiful theory, so far has only two very weak supporting evidence. So a new instrument will be able to provide more evidence for that or against that. Okay. Well, it won't be 100% against that. Otherwise, it will be as surprising as the American presidential election. Okay. And so, but there could be some details that one should try to work out. All right. So this is another important issue. This is related to our knowledge of the origin of all the elements. And then, for continuum, there are a lot of objects, compact objects, basically, emitting different kind of emission from infrared to, from radio to gamma rays. And in particular, there are pulsars, there are anomalous X-ray pulsars, there are black hole binaries, and there are active galactic nuclei, and there are also gamma ray bursts. These are a lot of things. Each of them can be 1 hour talk. Okay, so I won't go into those details, but just to tell you, there are many interesting things that one can study, that one should try to understand. And also, polarization. Later you will see, I will explain to you, the detector to detect MeV photons is based on Compton scattering. Compton scattering actually is polarization dependent. That means if the incoming photons have some polarization, then we are able to measure that. And therefore, if we can measure polarization of MeV photons, MeV, okay, it's not radio, it's not optical, it's MeV photons. That would be very, very nice. And currently, there are some sources that are more likely to be detected with certain kind of polarizations, which include pulsars and pulsar wind nebulae, and also gamma ray bursts. So if we can have some measurement of polarization, that will tell us the information mainly about magnetic field configuration in the system. Okay. So these are roughly the major things that we want to discuss, and this is the only slide that I have with so many words. Okay, other slides will be full of pictures. Well, before leaving this slide, I want to emphasize again, for this thing, nuclear synthesis gamma rays, this actually has something to do with supernova, and in particular with supernova type 1a, because supernova type 1a is used as standard candle to calibrate the distance determination. And in supernova type 1a, of course, we expect there are different lines which should be detected. And this is a way to check those models, to check whether the theoretical understanding of the current theoretical understanding of supernova type 1a is really consistent or not, and to use it as a standard candle, whether there is any problem, blah, 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 and so on. So this can be checked with the measurement of their nuclear lines. If we have a supernova type 1a event, which measure the lines. But unfortunately, as I said, so far, all the nuclear synthesis gamma lines have only two weak detection. One of them is supernova type 1a. I will show you that picture. Okay, but this is an important thing. And another possibly important thing is this GRB. GRB, well, the mainstream opinion is that there are two kinds. One is long, so another one is short. That's easy, right? And then, I think for the short ones, well, the popular model is that it's due to a merger of two neutron stars. And a lot of people expect that during this kind of merger, neutron star merger, there should be some detectable gravitational waves. So in this case, because now we know there are already some successful example of gravitational wave detection, right? So if one can have at the same time another counterpart in electromagnetic waves, I mean the same direction, blah, 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 then we can know much better the nature of that system which emit the so-called gravitational waves, right? So to monitor GRBs has this kind of possibility to provide electromagnetic counterparts to gravitational wave sources. So this is also quite important in the coming years. All right. So still one more fundamentals. To detect MeV gamma ray photons, we won't use optical telescope, right? So this figure show you that in order to detect photons, we need to rely on the interaction between matter and photons. The matter is our detector. So the x-axis is photon energy. The y-axis here is the atomic number of your detector material. And then, so for low energy photons, the photoelectric effect is the dominant channel for this kind of interaction. So one use some material to absorb photons in order to detect that photon. Okay. For high energy, typically pair production, electron-positron pair production is the dominating channel for the interaction. So people use pair production, electron-positron pair production to detect the incoming photons. And then at the energy somewhere in between around MeV, Compton scattering is the dominant one. So it's more logical to use this effect to design a detector to detect MeV photons, because the cross-section is higher, so that you can have higher sensitivity, larger cross-section effective area. So that's why I will talk about an instrument based on Compton scattering to detect the energy and the incoming direction of the incoming photons. Okay? All right. So the technology is like this. Long time ago, in the last century, this is during 1990 and 2000, there was a NASA mission called CGRO, Compton GRO Gamma Ray Observatory. And On that satellite, on that observatory, there are 4 instruments. One of them is called Compton. Compton is basically sensitive in this MeV energy range. And then the technology used at that time is that one has 2 layers, 1 layer and 2 layers of material. If there is an incoming MeV photons coming in here from this direction, that photon can scatter off some electrons in this material, and then the photon will go to another layer to be absorbed here. By measuring the location of these 2 interactions, and also the energy of the recoiled electron of the recoiled electron, then one can try to decide the energy of the incoming photon and also the direction within some constraint, within some cone. One can do that. And this is the technology used at that time. And you can see, well, photons can go to any other direction, right? They don't have to follow our design, right? Okay, so and also this whole thing from here to here is about 3 meters long. So it's a huge detector and a very small acceptance angle, so that the sensitivity is not really that good. So the point here for our detector, we use high purity germanium as the detector material at the right hand side here, and then for any incoming photon, again, Compton scatter somewhere, maybe multiple scattering, that's quite possible, somewhere, and maybe 3 or 4 events, and then absorb or escape. Okay. So with this kind of design, we can have a more compact detector. And later I will show you the performance. The performance is better than this one for a very small one. Small, as the drawing here. Later I will show you some more detailed pictures, but just for your information, that this is the current detector that we have is that 8 centimeter by 8 centimeter, and then the thickness is 1.5 centimeter. And for this configuration, we have 12 detectors here. Okay, so this is our detector, the basic principle of our detector. Okay, all right. So the purpose is to determine the direction and the energy of the incoming photon. So blah, 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 blah. So you can use all these relations and then try to infer from the measurement of the location of the interaction and the energy of the electron, recoil electrons. Then you can determine the direction within an angle. We can, it can only be determined within some cone. And therefore, for each photon, we have a cone. We have cone in the sky. And then suppose if there is one source only, then you expect that all the cones will intersect at one point. Okay, and so after you collecting all the data, you have to reconstruct the event. So it's not quite easy because in the sky there are not only one source, right? There are a lot of sources. So the lesson is that the life is not easy. Okay, and we still have to do some imaging processing, some no matter you believe it or not, we need to do some imaging processing. Okay, so the detector, the issue in this business is sensitivity, because Compton scattering, as you probably can see, is not so straightforward to have an image. And so the sensitivity is always the biggest issue in this field. With very low sensitivity, so we don't have strong detection of those lines. We don't have very good pictures, very good images with much high confidence. So here, our detector is like this. To determine the location of the interaction, this is one piece of detector. So if there is an interaction in the detector volume, on both sides of the detector, we have stripped electrodes, and they are in direction orthogonal to each other. On this side is this direction, and on the back side this is a mirror, and it's is in the other direction. So that when there is an interaction here, and if we apply a voltage on both sides, then we can detect signal on some strip. Then we can determine the x and y location of this interaction. And for the location in the z direction, then we can use the arrival time difference of these two signals to determine the location in the z direction. Okay, that's more or less the idea. All right. And then, of course, from the signal, the strength of the electric signal, the pulse height of the current, then we can determine the energy of the recoiled electron. All right. So this is again the picture. So this one, with this one, probably you can see better. These are 37 strips, and this is the back side. Okay, and from here to here, 8 centimeter. 8 centimeter. 8 centimeter is half of my palm only. So you can see. These are fingers of someone. Fingers of someone. So just to show you how small it is. How small it is. One piece. Very small. And then, in our earlier mission, we used this kind of configuration of the detector. We had 10 pieces of detectors assembled into an array in this way. And we used this one for our 2009 balloon flight. But later, somehow we have more detectors, so we use 12 detectors. Okay. All right. Yes.
What's the occupancy of that strip?
Strip?
Yeah, strip. Why you have this kind of the gap between strip is looks like quite long.
Okay. So it's a 2 millimeter pitch, and the gap is 0.25 millimeter.
Why you cannot reduce that?
Yes, we can. I believe so. Yes, we can. But that should be another version. Yeah. Okay. Yeah. Good. So I have already explained to you basically the design, the principle that we use in this detector. I haven't shown you the performance. Okay. But believe me, it's quite good. Okay. And this is the collaboration now. This project is led by UC Berkeley. So on the US side, this is UC Berkeley's team. PI is Stephen Bobs, and there are some postdocs and students. Postdocs. And also, Rose Berkeley National Lab plays also a very important role. Our detector, the crystal, is made by a certain company. I forgot the name. And then, Mark Annan, they are in charge of doing the surface processing of this crystal to make all those electrodes. So that's a very important thing. And then after that, the detector goes to UC Berkeley, and then we put on all the electronics from preamp to the laser ADC and all the digital readout systems. Okay, and in France there is a group also is involved in this collaboration. They provide cesium iodide to be colorimeter and sometimes the shielding, okay, shielding to shield the whole detector. And on the Taiwanese side, this one is me, and we are in Tsinghua, and I have now 3 students working on this project. That's it, okay. And then in NTU, Zhang Yuanhan is also in this collaboration because Zhang Yuanhan and Lin Zhixun are the 2 key persons for all the readout electronics. Okay. And recently, Jerry Xiao also joined this team because we are trying to do the next generation electronics. We want to make all the electronics smaller. Okay. And then in this collaboration, actually, we have some earlier members. People come and go. They make different contributions, like